Hi everyone. So today we're going to be dealing with Newton's three laws of motion. Newton's three laws of motion fall under a branch of mechanics that deals with how forces affect objects' motion. And that particular branch is similar to one that we've just studied. Actually, it's a part of it. Our projectile motion falls under this branch of mechanics, and it's called dynamics. It's different than statics, where statics deals with forces acting on an object that are not moving. Dynamics are going to deal with forces acting on an object that is moving or is going to be set in motion or stopped in motion. And these laws were developed by the one and only Sir Isaac Newton, who had a particular fruit fall on top of his head that kind of gave him this idea that something is causing an acceleration of objects. Force, some type of force is causing this apple to fall out of the tree. So Newton's three laws of motion. First one we'll look at, and they're labeled very easily. Newton's first law, second law, third law. We'll take a look at the first law first. But before we do, a quick little review and a little bit of further diving into equilibrium, which has to do with net forces acting on an object. And as long as the net force acting on an object is zero, so this can be something in motion, but there's no net forces acting on the object, then that object has to be in equilibrium, or a state of balance. An object that is in static equilibrium is not moving, it's at rest. So we want to think static, rest. An object in dynamic equilibrium is moving with a constant velocity. Meaning that it's moving at a constant speed in a straight line. And a good example for this, I think, is the ISS, the International Space Station. The International Space Station is moving in equilibrium around the Earth as it moves with no net force acting on the station. It's moving around the Earth in orbit with no additional forces to keep it moving, nothing to slow it down. It is setting forth with a velocity of 17,500. I believe that is miles per hour. And it moves at that velocity until something speeds it up or slows it down. And that's going to lead us into Newton's first law. So this ISS space station is moving constant velocity, not quite in a straight line, but it is moving in a constant velocity around the Earth. And I suppose since the ISS is not moving in a straight line, it can't necessarily be in equilibrium. Speed's not changing, but one of the things that is changing with the ISS is the ISS's direction. Since that direction continues to change around a circular path, it's experiencing centripetal acceleration, which means its velocity is changing because of the direction. So the speed remains the same, but the direction is changing. So therefore, we are accelerating around the Earth. So Newton's first law states that an object will maintain a state of equilibrium meaning it will remain at rest or moving with a constant velocity unless that object is acted upon by an unbalanced force. give you an idea of what an unbalanced force is, an unbalanced force is a non-zero net force acting on an object. So a force outside of equilibrium that's going to cause a change in the motion of the object. This change in velocity produces an acceleration because the object's speed or direction of motion, or both, are changing. In the case of the ISS, this is the direction, which gives the ISS an acceleration, a centripetal acceleration around the Earth. Now, to help understand these laws a little bit better, we have to have an idea of what inertia is, and you've probably heard it before. But inertia is the resistance of an object to a change in its motion. And this is directly proportional to mass. There's a couple examples I'll use here. If you think of a toy train kind of moving down a straight track, let's say at 1 meter per second. So we have a train here moving at 1 meter per second. And we consider an actual train. This is not drawn to scale. I will put my clarifiers in here, toy and real. They're both moving forward with a velocity of 1 meter per second. So let's say the real one has a mass of 1,000 kilograms, and the toy has a mass of 1 kilogram. That's just to represent that the real train is significantly heavier than the toy train. But if I was to ask you to push that toy train off the track while it's moving forward, you probably would think that that would be relatively easy. It's light, it's not moving very fast, it should be easy to knock off the track. But if you think of the real train moving down the same track, or a track, at the same speed, and I ask you to push that thing over from the side here, so you're going to try and stand here and push it off the track so it can't roll forward anymore, you'd probably tell me that that's completely impossible. The reason is, the real train has significantly more inertia. And that's because it is 1,000 times, at least in this scenario, heavier than the toy train. So it's going to resist any changes in its motion because it is so heavy. It has a lot of inertia. Another example of inertia is seatbelts. So seatbelts are used because of this idea of inertia. If you think about it, if you don't wear your seatbelt and you, let's say you were to come into contact with a tree, as soon as the car hits the tree, the car is going to decelerate, but because you are not part of the car and you are essentially loose inside of the car, you will continue in motion at that speed until some other unbalanced force stops you, generally going to be a windshield or a dashboard. That will cause you to slow down. Once you actually use the seatbelt straps you to the seat, which is part of the car. You are treated as one object. So when the car decelerates by hitting the tree, you decelerate at the same rate as the car because you are connected together and is treated as one singular object. Now, Newton's second law says that when an unbalanced force acts on an object, the object is going to be accelerated in the same direction as the force. And I'll show you some examples of this on the simulator, which I'm going to try and do in a video after we finish these little bit of notes here. Now the acceleration that's going to be imparted onto the object is directly proportional to the magnitude of the unbalanced force and inversely proportional to the mass of the object. Meaning that a smaller mass will accelerate faster with the same force, and vice versa. Remember, the vector sum of concurrent forces acting on an object is called the net force. If we're using vectors, that's going to be our resultant there. This is also known as a resultant, depending on concurrent forces we're looking at. So we will call that net force, or F sub net. Be careful with a lot of this, a lot of these notations here. You're going to start to see a lot more. Make sure you're writing these carefully and including all of the sub wording, in this case net, in each of your variables. Now the equation that we're going to use is acceleration equals F net over the mass of the object. Where we see the acceleration is inversely proportional to the mass in the denominator and directly proportional to the force imparted on the object, which is in the numerator. And 1 Newton given to you here is equal to 1 kilogram times a meter per second squared. But another way to kind of think about that is that 1 Newton is the force that imparts an acceleration of 1 meter per second to a 1 kilogram mass. So 1 Newton is going to equal an acceleration of 1 meter per second squared on an object that weighs 1 kilogram. Newton's third law is the last one we'll take a look at for today. Newton's third law says that when one object exerts a force on a second object, the second object exerts a force on the first object that is equal in magnitude and opposite in direction. These two equal but opposing forces constitute what we call an action-reaction pair. And they're a pair of forces that are acting on opposite objects. They're not acting on the same object. And I'll show you in a second here an example. Another way to word this is that for every action force, there's an equal and opposite reaction force. You might hear it, Newton's third law, that way. It's kind of a shorthand notation for every action. There's an equal and opposite reaction. And ultimately, this means that a single force is not actually generated in nature. We're always going to have some reaction or reciprocal force being produced every time we have an applied force. Now, a good example of this is when a bat is hitting a baseball. And I'm going to try and draw this here. If we have a person swinging their bat at a baseball, and this bat is going to apply a 50 Newton force, so 50 Newton force onto the baseball is also going to apply a 50 Newton force back on the bat. Now they're acting on different objects. The action force of the bat is acting on the baseball. The reaction force of the baseball is acting on the bat. So it's important to note that they're acting on different objects. I think that's important to note there. If we disregard no other forces in this scenario, which we like to do in this class, the objects are accelerated in opposite directions as long as the forces are applied. So this baseball is going to accelerate outwards when hit by the bat, but the bat's also going to be accelerated as well. And it's going to be accelerated in the opposite direction that the baseball is being accelerated. Now I'm going to do a few examples of these. I'll do these in a separate video. I'm also going to show you, I'm going to try and attach a separate video here, or I'll try and show it to you in class, using the PhET simulators. I encourage you to check it out. It is the Forces and Motion Basic Simulator on the PhET website, and that's going to be under Sims and under Physics. You can test out each of these laws using that simulator, and I will be showing you that shortly in a different video.